Howdy, folks, and let us continue on in our journey to learn chemistry. We have just finished learning about Lewis structures for molecules, and now we want to get into something called molecular geometry. And what is molecular geometry? Well, it is the shape of molecules. Now, to do that, to begin with, I think we first have to understand something about bonding domains and non-bonding domains, which are nice tools to help us with molecular geometry. So let us consider ammonia. How many bonding domains and non-bonding domains does it have? Well, we need some definitions. What are bonding domains? Well, bonding domains are the number of atoms directly bonded to the central atom. Okay, and so let us think about something like X here. Let's say we have X and I have 3 Y's bonded to that, and I have an unshared pair. Let's say I have that. So what we do is we look at our central atom and we say how many atoms are directly bonded to it. Well, there's 1 atom, there's a second atom, there's a third atom. What about my unshared pair? Is that an atom? No. So we'd say that this has 3 bonding domains. Now, what are non-bonding domains? Non-bonding domains. Well, non-bonding domains are the number of pairs, that's important, pairs of unshared electrons on central atom. Now, what's an unshared electron? Oh, that means it is not bonded. It's not shared with another atom. So when we look at our last example again, let's draw that again. I have X, I have Y, 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 and a pair of electrons here. We look at our little central atom, and we say, hey, I've got 3 atoms bonded. Those are my bonding domains. And then I have an unshared pair down here. This is my non-bonding domain. So I'd say I have 1 non-bonding domain. And you can see I'm using abbreviations. BD for bonding domain, Z, and NBD for non-bonding domains. Cool. Now let me show you let me ask you about one other example. What if I had X, Y, 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 we'll call this not Y, we'll call it Z. Z with another X on it. And we want to know my bonding and non-bonding domains on this. So we'd say, hey, how many atoms are directly bonded to my X? 1, 2, 3. What about this X over here? Is that directly bonded to this X? The answer is no, it's not. So we don't even worry about that. We still would say this has 3 bonding domains, and 1 non-bonding domain. We're only looking at what is directly on our central atom. Great. All right. Oh, we better answer our question, shouldn't we? Ammonia. First thing we want to do is draw our Lewis structure for ammonia, and it would look something like this, right? Let's take a look at my central atom. How many atoms are directly bonded on it? 3. So I have 3 bonding domains. And how many unshared pairs are on it? 1. Then be 1 non-bonding domain. Piece of cake. Jawohl, here we go. You try this one, pause me, bring me back when you're ready. Well, first thing we want to do is draw our Lewis structure. 6 valence electrons, 2, so I need 8 valence electrons. Oxygen in the center, bond it to my hydrogens, complete my octet on my oxygen. Now, let's analyze my central atom. How many atoms are directly bonded to it? 1, 2. So that's 2 bonding domains. And how many unshared pairs are on it? 1, 2, 2 non-bonding domains. So I'd have a 2, 2 answer. A 2, 2 answer. Ha! Here we go now. Now we get into the meat, right? I have ammonia, carbon tetrachloride, and selenium tetrabromide. What is the molecular geometry for each? Okay, let's take some notes. Molecular geometry. Well, first thing I want to know is, what is molecular geometry? What? Well, it is what? Really, we're talking about the shape of the molecule, and specifically we're really talking about the shape of created, let's go this way, the shape created by atoms bonded to a central atom or central atoms. Okay, that's what we're talking about. It means we're really not talking about the shape of the electrons. We're talking about the shape of the actual atoms bonded to this central atom, the shape that is created by that formation. Good. Now, how are we going to do that? We are going to use something called VSEPR, valence shell electron pair repulsion theory. VSEPR, valence shell. So we're talking about the valence shell, electron pair. So we're talking about pairs of electrons. And what do? They repel each other. Repulsion theory. And this is what? We are going to predict molecular shape, molecular geometry. And how are we going to do that? Based on the repulsion of electron pairs, specifically valence electron pairs, on a central atom. And the idea behind this is, hey, what's the relationship that electron pairs have? Electron pairs have what? They don't attract each other, they repel each other. So why, if I had an atom like X, would all of these electrons stay up here? The answer is they wouldn't. They don't want to hang around. They don't want anything, but nature doesn't have them hang around. What are they going to do? They're going to try to get as far away from each other as possible. And based on that concept, we could say that this would end up being something that we'd call, hey, trigonal planar is the shape, and they'd have 120 degrees between each electron pair. Okay, cool. Now, so that's the basis. Yoink. And what's the process? So let's talk about the process. What process should we follow? Here's the process. Number 1, draw your Lewis structure. By this time, you should all be experts in drawing Lewis structures. Number 2, determine number of bonding domains and non-bonding domains. Hey, now I understand, Mr. Smith, why you had us do that last exercise. Right, bonding domains and non-bonding domains are critical for us, because then what do? We find, or we get shape using bonding domain and non-bonding domain from chart. Hey, there's a wonderful chart. Now here's the good news, there's a wonderful chart. Now there's the bad news, in your head. You're going to have to memorize this chart eventually. So you're going to be able to use your bonding domains and non-bonding domains, and then in your head with your photographic memories, you can find that chart and say, aha, it is trigonal planar. Got it? Cool. Now, specifically, what is that chart? Well, let's make the chart. Here's the chart. Bonding domains, non-bonding domains, shape. All right, if I have 2, 0, it is linear. If I have 3, 0, we call that trigonal, and trigonal means it has a triangular base. Trigonal planar, planar means it is in one plane. 2, 1, it is bent. And we'll have a couple bents. 4, 0, this is very popular. It is tetrahedral, very popular with carbons, tetrahedral. Good. 3, 1, trigonal, trigonal, pyramidal, pyramidal. Some people call it trigonal pyramidal. What does that mean? It means it has a triangular base, and it makes a pyramid out of that triangular base. You know, yoink, yoink, yoink. There's my triangular base. It goes up to one spot of pyramid. Beautiful picture. Yee. You can see why I chose science instead of art. 2, 2, that is bent. Moving forward, we go to 5, 0. This is trigonal, another triangle, right? Trigonal by pyramidal or pyramidal, pyramidal, which would mean I take that pyramidal base, beautiful pyramidal base, point up, point down, yoink, 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 dee 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 dee. D, 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 D. There you go. 4, 1. This is what we call a seesaw. 3, 2. T-shaped. 2, 3. 2, 3. Linear. Oh, thank goodness. I can draw a linear. Yoink. 6, 0. Octahedral. 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 How about octahedral? There we go. Octahedral. 8 sides, right, with a square base. 5, 1. Square pyramidal. Pyramidal. And finally, 4, 2. And this is what we call square planar. Okay, so how many of these do you have to memorize? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So you need to memorize 13 shapes based on 13 different arrangements of bonding domains and non-bonding domains. Good. Now, let's take a look at what these things kind of look like. Thanks to our people here at Pearson Prentice Hall, they have a beautiful picture here. We want to look at our bonding domains, non-bonding domains, and molecular geometry. Over here, we don't care about yet. So let's just focus on the center of the board. 2, 0. This is what a linear looks like, and we're talking about my atoms, how they arrange. 3, 0. Trigonal planar. That means I'd have a central atom here and 3 atoms around it, and it makes a triangle in one plane. 2, 1, bent. Now notice, we look at the bent shape and we ignore our unshared pair. We're just looking at the shape of the atoms, right? We're looking at the shape of the atoms around my central atom. 4, 0, tetrahedral. That's what a tetrahedral looks like. Far better drawing than I make. Trigonal pyramidal. Here's trigonal pyramidal. 3, 1. Hey, my drawing wasn't half as bad as I thought it was it? 2, 2. It is bent. Yeah, there we go. Bent. Remember, we're only looking at the arrangement of the atoms. Trigonal bipyramidal. 5, 0. Here's trigonal bipyramidal. Looks kind of like that. You know, it's like a line and then a triangle in space. If you put the atoms over here, and some of you could say, wow, it looks nothing like that, Mr. Smith. Yeah, you might be right. Seesaw, 4, 1. And that doesn't look anything like a seesaw unless you turn it on its side. And then it kind of looks like that. And then it looks like a seesaw. Cool. T-shaped, yeah, T-shaped on its side. 3, 2. Linear, whoo, thank goodness. There's linear again. We can handle linear. 6, 0. This is a octahedral. We have a square in one plane, and then you have 2 atoms apart from each other going through the other plane. If we really looked at the shape it makes, apparently it's going to make what? An octagon, an octahedral. 5-1 square pyramidal. I have a square base going up to 1 point. That makes it a square pyramid. And then 4-2, that is square planar. And it's just really a square in one plane, two-dimensional square. All right, can we answer our questions? Consider ammonia, carbon tetrachloride, and silicon tetrabromide. First thing we must do is what? Lewis structures. So ammonia looks like this, right? How many bonding domains does it have? Bonding domains. How many non-bonding domains does it have? Okay, bonding domains, 1, 2, 3. 3 bonding domains, 1 non-bonding domain. Shape, it is a 3-1. Let's look at our chart. What is a 3-1? A 3-1 is 3-1. It is what? Trigonal pyramidal. There we go. Trigonal pyramidal. Trigonal pyramidal. Good. Next, carbon tetrachloride. We have to draw our carbon, our chlorines, right? And we should all be experts at this. Now, I should be careful, right? 4 and 28, I should have 32 electrons in my picture. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Okay, so my picture is right. Let's look at my central atom. How many atoms are directly bonded to it? 1, 2, 3, 4. I have 4. Now, how many pairs of electrons are on my carbon? These guys out here don't count on my chlorine. I'm just looking at my carbon. How many unbonded electron pairs do I have there? And the answer is 0. So I have a 4-0. When you look at 4-0, what do we have here? 4-0 is tetrahedral. 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 Good. And the last one, we have selenium tetrabromide. Selenium tetrabromide. Okay. Selenium tetrabromide. Good. Now I better count my valence electrons. 6 and 4 times 7 is 28, 34. I need 34 valence electrons. 34 valence electrons. So let's complete my octets. And count 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So I have 32 electrons. But how many do I need to have? I need to have 34. So that means I need to add 2 more electrons. Where do they go? They go on my central atom. Good. So now, let's get rid of my 32 here. So look at my central atom. How many atoms are directly bonded to it? 1, 2, 3, 4. So I have 4. And how many unshared pairs do I have on it? 1. I have a 4-1. Let's look at my chart. What is a 4-1? 4-1 is what? Seesaw. Okay. So let's write down seesaw. Seesaw. Good. Think you guys can do it? I think you can. Here you go. Consider these 3, nitrogen, bromine tetrafluoride, and boron trifluoride. Pause this. When you're done, bring me back. Okay, some of you might have had a little bit of a problem with nitrogen, and you're going to slap yourself when you realize the answer here is when I look at my bonding and non-bonding domains, we'd say what? It's a 1-1. I have 1 atom bonded to my nitrogen, and it has 1. If I look at that atom, I have 1 atom and 1 non-bonded domain, and you'd say, hey, here's my bonding domains, non-bonding domains. We don't have a 1-1. Well, anytime I have only 2 atoms, what's it got to be? If I only have 2 atoms, it is always linear. Yeah, Mr. Smith, Why are you so mean? Okay. Bromine tetrafluoride, pentafluoride. So that's 7, and then 5 times 7, that's what, 42? So I have to have 42 electrons in my picture. Fluorine, 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 doink, 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 doink. Do, 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 do. Good. Let's count them up. 2, 4, 6, 8, 16, 24, 32, 40. I only have 40. That means I need 2 more here. There we go. That's my picture. Remember, you have to draw your picture first properly. Here's my central atom. How many atoms are directly bonded to that? 1, 2, 3, 4, 5. So that's a 5. And how many unshared pairs? 1. That's a 5, 1. We go to our beautiful pictures. What is a 5, 1? A 5, 1, a 5, 1. 5, 1 is what? Square pyramidal. 5, 1 is square pyramidal. Good. And boron tetrafluoride. Boron has 3 valence electrons. My fluorines each have 7, make 21. I need 24. Excuse me, electrons in my picture. Boron, fluorine, fluorine, fluorine. Bond that there. Good. Complete my octets. Do I complete my octet on a boron? No. Boron wants how many electrons? 6. Does it have 6? Yes, it does. So now we count. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. 24 electrons. That's a beautiful picture. Let's focus on our central atom. How many atoms are directly bonded? 1, 2, 3. Any unshared pairs? No. This is a 3, 0. And when you look at our chart, a 3, 0 is trigonoplanar. Trigonoplanar. Okay, excellent. Let's do one more quickly, and I'll just run through this to show you. Okay, this one's difficult because it is very complex. It has more than one central atom. And the Lewis structure for it is this. Okay, and then we need to put some more electrons there. Good, 2, 4, 6, 8. There we go. So this is what my Lewis structure for acetic acid looks like. And so the question is, Mr. Smith, how do I know the shape of this? Well, really, there is not one shape. There are 3 shapes because this is a central atom, this is a central atom, and this is a central atom. So I have a shape around this carbon, a shape around this carbon, and a shape around this oxygen. Well, what's the shape around this carbon? This first carbon, I have 1, 2, 3, 4. It's a 4, 0. That means it is tetrahedral. Tetrahedral. Good. What about this carbon in the middle? I look at it and I have what? Well, let me go with a different color. This carbon here, I have an atom bonded here, an atom bonded here, and an atom bonded here. Do I have any unpaired electrons on it? No. It is a 3, 0, meaning it is trigonal what? Planar. It is trigonoplanar. And what about my oxygen? Thank goodness we have all kinds of colors. Let's look at this oxygen here. 1 atom, 2 atoms, so it has 2 atoms, and it has 2 unshared pairs. It is 2, 2, and when we look at our chart, it would be bent. So that's how you handle something that is more complex. You have to look at every central atom and get a shape around every central atom. So this is tetrahedral around the first carbon, trigonoplanar around the second carbon, and bent around the oxygen. All right. Thanks for the time. We will see you next time. Hi ho.